Good afternoon, students. Welcome to our lesson 4. And before I get into our next lesson, I just want to recap what we did yesterday, which was the introduction into the molecular kinetic energy, and we related human or yeah, human kinetic energy, which is a half mv squared, and we related that to atoms because they move so fast, they have kinetic energy. And we also looked at the factors that affect molecular kinetic energy, which are temperature, volume, and pressure. And we also said that scientists have derived laws to relate molecular kinetic energy to chemical reactions. So that is what we're going to look at today. We're going to look at our three laws derived by three different scientists, which relate temperature, pressure, and volume in a chemical reaction. So that is the gas laws, and the first gas law that we're going to look at was derived by Boyle, and that is Boyle's law. Now, Boyle's law relates volume and pressure in a closed system. Now, a closed system can be defined is a system that has no external forces or stimuli acting on it. So, an example would be a hot pot that is sealed with sellotape. The heat is being generated by the pot, but nothing is coming in and nothing is going out. So that is a closed system. Now, Boyle's law states that in an enclosed mass of gas, the pressure of the gas is inversely proportional to the volume, provided the temperature remains constant. This means that Boyle's law will not work if the temperature is changing. And it also means that if the pressure of the gas increases, the volume will decrease. And if the volume increases, then the pressure will decrease. And this is the proportionality, which in equation form says that the pressure is inversely proportional to the volume. And this is a graph to show that you can see that volume is on the x-axis and pressure is on the y-axis, and at a small volume we have a large pressure, so that's 15 volume units, and that would correspond to just 119 pressure units. And remember, yesterday we said that pressure has many units. It has millimeter per mercury, it has pascals, which can be converted to kilopascals, and it can be used. And one of the other units of pressure is atmospheres. So it can be any one of those pressure units. So, and then we look down, that's 48 volume units, and that corresponds to um, around 30 pressure units. So we can see that as the volume is increasing, the pressure is decreasing. So how do we use Boyle's law? Well, Boyle derived an equation that we can use to calculate pressure or volume changes in a reaction vessel, and this equation is P1V1 equals to P2V2, where P1 is the initial pressure, V1 is the initial volume, P2 is the final pressure, and V2 is the final volume. Now I didn't put any um, units here because there isn't a standard unit that can be used. If V1 is given as cm cubed, then V2 the answer will come out as cm cubed, and if pressure P1 is given as kilopascals or atmospheres, then P2 will come out as kilopascals or atmosphere, and we'll see that now. So the first example that we're going to look at is a sample of helium gas is compressed from 4 liters to 2 liters at a constant temperature. If the initial pressure, was 3 atmospheres, let's change that quickly. If the initial pressure was 3 atmospheres, what is the new pressure at 2 liters? So our volume is decreasing, so that gives us an indication that our pressure needs to increase. Okay, so the first thing we're going to do is we're going to write out our equation, and that's P1 V1 equals to P2 V2. Now we're going to substitute our values. That is 4 liters because it was compressed from 4 liters to 2 liters, which means our volume is decreasing. So that's 4 liters into 3 atmospheres equals to P2, which is what we're calculating, multiplied by 2 liters. And we rearrange the formula to get P2 as the subject. So we divide by 2 liters on both sides, and P2 equals to 6 atmospheres. Now we know our answer can be correct because our volume decreased, and by Boyle's law, since it's an inverse proportionality, our pressure had to have increased. So that is Boyle's law. So the next law we're going to look at is Charles' law, and Charles' law related temperature to the volume at a constant pressure. Okay, and the temperature uses the Kelvin scale, which starts at minus 273 degrees Celsius, and we'll look at that in the next slide. Now, Charles' law states that in an enclosed mass of gas, the temperature of the system is directly proportional to the volume, provided the pressure remains constant. Two things again is that we cannot use Charles' law when the pressure is changing, and the second thing we know is that if the temperature increases, the volume will increase, and if the temperature decreases, the volume will decrease. So that is our proportionality equation, which we'll use to derive our Charles' law equation. And there is a graph, there is a straight line graph of Charles' law, and we can see that the temperature is on the x-axis in Kelvin, and we have volume in milliliters on the y-axis, and we can see that as the temperature increases, the volume increases as well substantially. So the Kelvin scale. The Kelvin scale starts at minus 273.16 Kelvin degrees Celsius, and that is a point called absolute zero. Now, at 0 degrees Celsius, it is 273.16 Kelvin. Okay. Now, if we want to convert our degrees Celsius to Kelvin, all we have to do is take 273 and add it to our degrees Celsius temperature. So as you can see there, the temperature was 100 degrees Celsius, and they added 273.16 to get our degrees in Kelvin. Okay, so how do we use Charles' law? Well, we use it to calculate temperature or volume changes in a chemical reaction vessel, and there is an equation for that, and that is T1 over V1 equals to T2 over V2. Now, in this equation, the volume units do not matter. So you could have meters cubed, you could have dm cubed, you could have cm cubed. It doesn't matter. Your answer will come out in any units that you have. You could even have liters and your answer would come out in liters. But please know that your temperature has to be in Kelvin. If it's not in Kelvin, you will get your answer wrong. So please make sure that it is in Kelvin. So that's our equation. T1 over V1 equals to T2 over V2, where T1 is the initial temperature in Kelvin, V1 is the initial volume, T2 is the final temperature in Kelvin, and V2 is the final volume. Now let's look at an example. And our example says a sample of chlorine gas is compressed at a constant pressure from 120 cm cube to 70 cm cube. The initial temperature of the system was 45 degrees Celsius. Calculate the new temperature in Kelvin at 70 centimeter cube. So we know that our volume is decreasing, so it gives us a general idea that our temperature should decrease as well. So first thing we need to do is calculate our temperature in Kelvin. So we're going to use 273 for easy purposes, and that's 273 plus 45 because that was our initial temperature, and that gives us an answer in Kelvin, which is 318. So next step is we write out our equation, which is T1 over V1 equals to T2 over V2. Now we substitute our values, and T1 is 318 Kelvin, and V1 is 120 cm cube, which equals to T2 over 70 cm cube, which is our final compressed temperature volume. We rearrange our formula to get T2 as the subject by multiplying both sides by 70 cm cube, and our answer should be 185.5 Kelvin. Now if the maths is correct, we know that our answer is correct because our temperature decreased as well. So these examples and problems on the gas laws are quite easy to predict. If you know that your volume is being compressed, then you should know that your temperature is decreasing as well. So in a test or an exam, if you get a higher temperature than what you would expect, then you need to go back and double check your work. Moving on to Gay-Lussac's law, and Gay-Lussac's law relates the temperature and the pressure at a constant volume. So notice how Boyle's law kept it at a constant temperature, Charles' law kept it at a constant pressure, and Gay-Lussac now kept it at a constant volume. Okay, so Gay-Lussac's law states that in an enclosed mass of gas, the temperature is directly proportional to the pressure provided the volume remains constant. And this means that our temperature, if it increases, our pressure is going to increase, and if our temperature decreases, then our pressure will decrease at a constant volume. Okay, so that is our proportionality ratio, which says that P is directly proportional to T, and that is a pressure uh, versus temperature of, and it represents Gay-Lussac's law. It is a straight line, and we can see that as the temperature increases, the pressure increases. So you could get an investigation type question where you'll have to be asked to draw a graph, or you'll have to be asked to gather data from the graph, and you'll have to determine whether Gay-Lussac's law or Boyle's law or Charles' law is being obeyed. Okay, so how do we use Gay-Lussac's law? Well, it is the same as the other two gas laws. We use it as an equation to calculate the temperature and pressure changes in a chemical system using the equation P1 over T1 equals to P2 over T2. Now, just like Charles' law, the unit for the pressure does not matter. You could have atmosphere, you could have kilopascals, you could have pascals, but the temperature has to be in Kelvin. Okay, so P1 is the initial temperature, T1 is the initial temperature in Kelvin, P2 is the final pressure, and T2 is the final pressure in Kelvin. So, lastly, for this lesson, or last example, is a sample of gas was heated at a constant volume from 18 degrees Celsius to 40 degrees Celsius. If the initial temperature, if the initial pressure, sorry, change that quickly as well. If the initial pressure was 2000 pascals, what is the final pressure after the gas is heated? So the first thing we need to do is we need to calculate our temperatures in Kelvin. So T1 equals to 273 plus 18, and we get an answer of 291 Kelvin. And T2 is 273 plus 40, which equals to 310 Kelvin. Now from Gay-Lussac's law, we say P1 over T1 equals to P2 over V2. We substitute our values in, and we rearrange the formula to get P2 as the subject of the formula. We do our maths, and our answer is 2130.58 pascals. Now, because our temperature increased, we can see that we have a pressure increase, which means Gay-Lussac's law is being obeyed. Now, very quickly, we're going to look at some real-life applications of the law. And Gay-Lussac's law is applied when heating an aerosol can. So if you put a deodorant can into fire, you're heating the deodorant and you're causing the deodorant particles to hit the can much more often, and that would increase the pressure. And if you do that, then the can would explode. Okay, so please don't do that. It is a safety hazard. So, but that is an application of Gay-Lussac's law where there is a temperature and pressure change. Charles' law is applied when you leave a ball outside on a cold day, so the ball becomes hard or it becomes soft, or it becomes hard and it becomes smaller. Okay, and the last one is Boyle's law, is when you put pressure into a tire. You're increasing the pressure in the tire, so the temperature is kept constant, and yeah. So that is all for today's lesson. If there are any questions, please feel free to email me. The homework will be uploaded onto Google Scholar, and we will see each other in the next lesson. Thank you. Bye.